Okay, good morning. Shall we start? So you can pick up the quiz 1 and also the research test at H113, that's in the Honkan over there. And we are going to have the next quiz 2, on Wednesday, that is the day after tomorrow, okay, December 19th. So at that moment, at the time of the quiz 2, you can also resubmit or late submit of your quiz 1. Okay, so quiz 1 is available here. So if you didn't have a chance to take that quiz 1, you can pick up the sheet and then write your solution and submit it. Okay, so in the Moodle there is also a solution posted, so you can just check against the solution. And also, if you didn't get 5 points or above, then you can also say correct or add solutions to your quiz 1 and then resubmit it at the time of quiz 2. Okay? So in the Moodle, you have lots of information. And if you have any problem, for example, watching the screen capture movie, then please let me know. I also recognize some difficulty, say, watching the movie, but in some means it's possible. So if you have difficulty watching the screen capture video posted in the Moodle, then please let me know. Today, we have only one. Okay. So I received the quiz 1 here, but I don't want to receive today. Okay, please take it back. If it's okay for me to just lose it, then I can accept it. But you have a risk that I may lose your quiz. Very high risk of losing the quiz 1 if I get it some other day. Okay? Not in a specified date. Okay, so let me see. It says comment sheet, check Moodle. So I think some of you already know that in the Moodle, I've written some of my responses to your comments. So please take a look at it. Okay, I think some of you didn't ask any questions written on the comment sheet, but some other students may bring up some difficult, important questions. So in that case, those responses to those questions may help you understand the contents of the lecture. Okay, and also we provide a help desk that is 1:20 to 4:20 p.m. Monday and Wednesday at Science Hall, South Wing of the 3rd floor, 302. So if you go there, there is Dr. course students waiting for you to assist you. Okay, and you can use the Khan Academy or the e-college material posted in the internet, and there is a link from the Moodle. Okay, you can use those materials, and which section you should look at is written in the Moodle. And I haven't checked the link this year, but I will check it, and so that you can reach the correct link to the related sites of the Khan Academy and e-college. So quiz 2, system of linear equations, as it is written here. You can study old quizzes and so on. Okay, but I think if you just understand the exercises and the old quizzes included in the handouts, then I think that will be fine. So let me start the review. So the matrix is an n by n rectangular array of numbers, and B is also, this type of thing is also called n by 1 matrix. Okay, there are m entries. And the topic we are dealing in this section is the system of linear equations. System of linear equations is the system of equations like this, and x1 to xn are unknowns or the variables. And in this case, there are m equations with x1 to xn n unknowns. And linear means the power of the unknown part, x1, x2, are just the power at most 1. Okay, so you may have the constant term, but no higher terms like x1 squared or x1 cubed. So these are the typical examples of the system of linear equations. So I think in high school or junior high school, you use the variable to be x and y. Okay, but since we are going to talk about the general form of system of linear equations, which may have many variables, like 10 variables or 20 variables, and so on. Okay, so that's why we sometimes use the variable using the indexed variable, like x1, x2, x3, in this case, up to x6. Okay. So solution is kind of clear, but in this case, x1 to xn, if you have n variables, then you have a sequence of n numbers. And if you substitute s1 to x1, s2 to x2, and sn to xn, and if the equation part becomes a valid equation, okay, correct equation, then that is called the solution. Okay, so for example, in the left-hand side, left bottom equation, if you put a plug 8 in x and 2 in y, then left-hand side and right side are equal. So we say that 8, 2 is a solution. Okay. And in some cases, for example, in this example, if you plug 1, negative 1, 1, or 0, negative 2, 3, then both of these sequences satisfy the equation, system of equation. That means the solutions are more than 2. Okay? So we want to find out a way to express all solutions. All solutions are called the general solution of the system, okay, as it is written here. Or we also call it the solution set. Okay, we just introduced the set a little bit in the first section. Okay, so the solution set is a collection of all solutions. We will introduce how we can describe the solution set or the general solution. Okay, I said that I introduced the word equivalence. Okay, if the two system of linear equations, in this case, the left-hand side and right-hand side, these two are called equivalent because the solution set of the left-hand side equation and the solution set of the right-hand side equation, you can tell if you work out a little bit, then you can tell that the x is equal to 8 and y is equal to 2 is the only solution to both of the system of linear equations. Okay? And when the solution set are equal, we call them equivalent. And we want to, say, modify the system of equations a little bit, little by little, just by keeping the equivalent system. That means we just want to keep the solution set equal and just change the form of the system of equations to an easier system of solutions so that we can find the solution easily. Okay? All right? But the things are not so easy. Okay? We haven't worked out the second set of equations, but for the first one is written somewhere here also, and we will explain it again. The first one has infinitely many solutions. Okay? The first one has infinitely many solutions, but the second one looks very similar to the first one, but the second one has no solutions. Okay, so first thing we have to do is to determine whether the system of equations, system of linear equations or linear system has a solution or not. Okay, if the system has a solution, we call it consistent. If the solution does not have any solutions, then we call it the system is inconsistent. Okay? So the first one, as you can see, that the 1 minus 1, 1 is a solution. Without knowing the second solution, we can just say that the system is consistent. Okay? For the second one, from this, we cannot tell whether it's consistent or not, but we will see later, hopefully. The second one, say, does not have any solution, so the second one is called inconsistent. And we started out thinking about basic or fundamental questions about the linear system. Okay, so one of them is the system consistent? So our concern is whether the system has at least one solution or not. Okay, if it has a one solution, then we call it the system is consistent. Otherwise, inconsistent. And if a solution exists, okay, that means if the system is consistent, we want to ask the next question. Is it the only one? Is the solution unique? So in linear algebra or in mathematics, it's often the case. If we say the solution is unique, that means not very special solution, but there is only one solution. Okay? If you use the word unique, okay, that means there is only one solution. If more than one solution exists, that means if the solution is not unique, then how can we describe the solution set? In the first example, we know that there are at least two solutions. Okay? Then can we describe all solutions in some way? Okay? And for example, this one, you have two sets of complicated system of linear equations. Okay? So firstly, we have to identify the number of equations and the number of unknowns. Okay? In this case, clearly, both of the system have 6 unknowns, okay, because the x1 to x6. Okay? There are 6 unknowns and 4 equations. Okay? The right-hand side is non-zero. That is also important, but I will explain it, I think not today, but later. Okay? So we want to ask whether it's inconsistent or solutions are unique if it exists. Okay? Inconsistent means there is no solution. So in order to do it, okay, we introduce one way to solve it. Okay? And I want you to learn this way of solving the system. This can handle all possible system of linear equations. Okay? And also that gives or that provides the theoretical background we are going to discuss at the next section, which will start this Friday. Okay? So all these things are very important for the next topic as well. So I want you to learn how to solve the system of linear equations in this way. Okay? So firstly, we just construct an augmented matrix. Okay? That part we have already introduced. And elementary row operations. And then we bring it to the reduced row echelon form. And then find solution. Okay? We roughly introduced, say, the step 1, 2, 3, and briefly about 4. Okay? So we want to discuss these 4 steps in detail today. Okay? Let me start. So this is exactly the same system of equations on the slides and also on the blackboard. Okay? So firstly, we want to first write out the augmented matrix of the system. Okay, augmented matrix is something is added. Okay, so this A is the augmented matrix, and this consists of the numbers taken from the coefficients of the unknowns x, y, and z, and also the right hand side. Okay? So the coefficients of x are 3, 1, 11, and those numbers appear here. Okay? The coefficients of y, nothing is written. Okay, but then you can tell that the coefficient is 1, 1, and negative 1. That's why in this one is called second column. Okay? The horizontal one is rows, and the vertical ones are columns. Okay, so 2, 1, 5 are the coefficients of z, and then the right hand side is 4, 1, 17. Okay, and we also today, in order to write out the solutions, we want to think about the coefficient matrix as well. Okay, this matrix A is called the augmented matrix. Okay, and the right hand side matrix C is called the coefficient matrix. Okay, coefficient matrix is the part of the augmented matrix that is taken from this part. Okay, so those are the coefficients of the variables. That means we leave out the right-hand side part. Okay, so that is called the coefficient matrix. We're going to use both of them. Then I just want to skip the middle part, and then by the elementary operations, elementary row operations, we bring it to the reduced row echelon form. Okay, we will review that part later again. Okay, this is called the reduced row echelon form, and then so that means starting from this augmented matrix with a sequence of some operations, that is, they are called elementary operations, and then make it to a simple form, okay, and in simple and nice form, that is defined mathematically just as above, and this is called the reduced row echelon form. Okay, so change into a reduced echelon form. Then now we read out the solutions. But this is also an augmented matrix of a system of linear equations. So let me just, until you get used to it, okay, first write out the system of linear equations corresponding to this augmented matrix. Okay? Then you can find this. Okay? Firstly, if you have this, then you may be able to write the augmented matrix. Okay? But the important part is, for example, the second equation does not have x. Okay? That means we assume that the coefficient of x is 0. Okay? 0 times x plus y plus 1 over 2z. And here in the first equation, you can see y. Okay? So we assume that that is 0 times y. Okay? So then you can tell that this augmented matrix is corresponding to this system of linear equations. Okay? But the important thing is you have to go back and forth from the system of linear equations to the augmented matrix. And also from the augmented matrix, you want to write out the system of linear equations. And in this case, okay, now we last time, at the last moment, okay, I just told you the way to write out the solutions. Okay? Now, this is the augmented matrix. Okay, I will repeat it again later, but this type of the first non-zero entry from the left, okay, is 1, okay, because of the definition of the augmented. That is called the leading one. Okay? So in this case, there are 2 leading ones, and up to the third variable. So this is x, y, z. Okay, the rightmost column is for the right-hand side of the equation. Okay, so besides that, okay, though there are three variables that we have there. Okay, and then choose the variable, okay, which doesn't have the leading ones. Okay, the first one corresponds to x, the second one y, and third one for z, right? But the x and y column, you have leading ones. Okay? But for z column, you don't have leading one. Okay? Then choose this z for the free variable. Okay? Then using this free variable z, then you can write out x and y in this way. Firstly, let's look at this one and this one, corresponding. Check this one. The first one is the augmented matrix of this system of linear equations. The third row is the horizontal one, okay? 0, 0, 0, 0, so it's not written. Okay? If you want to write it, then this is 0 equals 0. Okay? So 0 equals 0 is redundant, but it doesn't have any special meaning, so I just left out that 0 equals 0. Okay? So you have this. Now, this is the solution. That means we want to read out the solution. And just let's think about it. Okay? So if you have some number for x, okay, then for example 1, okay, then you can solve for z. Okay? Let me just use the slide. Okay? We have this. Okay? So if you have x, then I think you can solve for z. Okay? And if you know z, then you can also solve for y. Right? So you can start from x and then come back to y as well. Okay? But if you just start giving some values for z, then you can get x and also y. Okay? So that is simpler. Okay? And if you start from x, then you anyhow have to solve for z, right? It's not so difficult, okay? So I think everyone can solve for z, okay? But anyhow, you have to solve for z. But if you start from z, if you give some number for z, then you can write the value for x very easily. And also, with that value for z, you can write the value of y. So if you choose the variable in a suitable way, okay, then you can find the solution very easily. Okay? And the reduced row echelon form is designed to have such things. Okay? And you also have to add one more thing. Z can be anything. 0, 1, minus 100, or pi, or square root of 2, anything. Right? Although x and y may be a complicated one, okay? But z can be anything, okay? Z can be anything. That's why we write z is free. Then we can observe one more thing. Z is free. Z can be anything. That means there are infinitely many solutions, okay? There are infinitely many solutions, right? Because the z can be 1, 2, 3, 4, 5, 6, and even 1.1, 1.11, 1.1111, 3.14 something, okay? Anything is fine. Also, the negative value is also allowed, right? So there are a bunch of them. Then we can tell easily that there are infinitely many solutions, okay? So in this case, you have an infinitely many solutions. Okay? So let me explain the procedure systematically, okay? So we first start from a system of linear equations, okay? Then we first construct an augmented matrix, the augmented matrix of the system, and also the coefficient matrix of the system, okay? The example is like this, okay? So you just have A and C, okay? But a C is just a part of A, okay? So you may not have to write out C part, okay? Then, for example, in this case, as I written over there, okay, I have written over there, augmented matrix is the one A, named A, and this coefficient matrix is the matrix named C, okay? And in this case, augmented matrix is this, and the coefficient matrix is this. Okay, let's just check it. Okay, so there are many zeros. Okay, so it's a little bit confusing, but if you carefully work out, I hope you can write out the augmented matrix and the coefficient matrix. The difference between the augmented matrix and the coefficient matrix is only the last part, last column. Okay, if you just cut off the last column of the augmented matrix, then you get a coefficient matrix. But that is natural, right? Because the last column of the augmented matrix is taken from the right-hand side of the equation. Okay? So that's why we just can have the augmented matrix. Okay, let me just check the bottom row. Okay, that is a fourth row. Okay, fourth row. You have the coefficient -2, -2, 2. So -2, -2, 2, and -6, -2, -4 equals -4. Okay, so that's why we have this. Okay. Now we want to use the elementary operation to obtain reduced row echelon form. Okay, and so the target matrix is the reduced row echelon form. Okay, so we have to know what that is. Okay, then that is written on the right hand side. Okay, but we're gonna use these three kinds of row operations. Last time I described it by words because in that way we can just describe it exactly. Okay, but this time I use the symbol like that. Okay, if you know the contents, it's kind of easier to just get image of it. Okay, so the replacement is written as I, comma, J, semicolon, C. Okay, that is just as it is written here. Row I is replaced by the sum of row I and C times row J. Okay, and then I, comma, J, that is an interchange row I and row J. So it's a swapping row I and row J. Okay, then I semicolon C multiply all entries in row I by a non-zero constant C. So row I is replaced in some way by C times row I. Okay, so you can see that this comma and semicolon, the distinction of the semicolon and comma is essential. Okay, because they, for example, 1, 2, 1 comma 2 and 1 semicolon 2 means completely different things, right? 1 comma 2 is swapping the two or interchange two rows, the first row with the second row. Okay, so what I'm saying is, okay, 1, 2, 1, 2, and 1 semicolon 2. These are different, right? 1, 2 is interchanging the first row with the second row. And the 1 semicolon 2 is the, say, multiply 2 to the all entries of the first row. Okay? Then, what is the target form of the matrix? That is the reduced row echelon form. Okay? So the leftmost non-zero entry is 1. So I just wrote a kind of the one of the rows. Okay, each row, okay, if there is some non-zero entry, then the leading entry, that is the first non-zero entry from the left. Okay, looking at from the left, then the first one has to be equal to 1. Okay, then the rest of them, that star mark, asterisk, means that can be any number. Okay. Then second item, all non-zero rows are above all rows of all zeros. Okay, so that means all non-zero rows are collected above all zero rows. Okay, so that means in other words, all zero rows are down below. Okay, then the third one, each leading one is to right of the leading one of the row above. So there are several places. We have one, leading one, okay? Then if you're going down, then that leading one has to go to the right, okay? So in that way, we have a kind of the stairs, okay? staircase like that. Then each leading one is the only non-zero entry in the column. Okay? So you have leading ones, then the entries above and below are all zero. Okay? But the other part we don't know. Okay? So now we want to reach that reduced row echelon form from the general form of the augmented matrix. In this case, in this particular case, okay, we wanted to reach the reduced row echelon form satisfying those four properties. Okay? Then starting from this, we want to have something on the farther left, 1, right? So anyhow, here is 1 here already. Okay, so we want to bring this one to the top left. Okay, so that's why we just first interchange the row 1 and row 2. Okay, now we have this one. So from here to here, first to second, I switch the first row with the second row. Okay, now since one, this can be the leading one, and we want to have zeros down below. Why is that? Because the leading one is the only non-zero entry in the column. Okay, column is the vertical one. Okay, so we want to get 0 here. How do we get it? Okay, there are two ways. One of them is multiply 0 all the way, but that is not allowed. Okay, please look at it. Okay, multiply all entries in row I by a non-zero constant c. Okay, so when you multiply some number all the way through, okay, in some specific row, then that number has to be non-zero number. Okay, so you cannot just multiply 0 here. Okay, so the other way, even if you just switch rows, you cannot get 1 here. So the only way you can get 0 here is to just subtract some number times some row from the to add to the second row. Okay, so in order to get this, since you have 1 here, so if you multiply -3 to the first row and then add to the second row, then you get 0 here. Okay. Okay, here you get 1, 2. But here, we wanted to eliminate this 3. Okay? In order to do it, what I did is 2, 1, minus 3. What does it mean? So this is, we replace the second row, okay? Second row, and then add the -3 times the first row. So just write the second row, and then -3 times the first row. That is -3, -3, -3, -3. And then add them together. Okay? Then you get 0, -2, -1, and 1. That is the one we have here. Okay? So you get that one. Then we also want to get 0 in this place. We have 11. Okay? In order to do it, again, multiply -11 to the first row and add to the third row. Here, nothing is written, so let me just try it. Okay? So from here, in order to eliminate this part, just looking at this part, so what you're going to do is say, we're going to replace the third row by third row plus the sum of the first row times -11. Okay, then the third row is 11 minus 1, 5, 17. Okay, and then -11 times the first row. First row is easy, so -11, -11, -11, -11, and add them together. you get 0 minus, oh, is something wrong? But that row, maybe okay. Minus 12, so add them together, minus 12, minus 6, and then 6. Okay, so you can write 0, minus 2, minus 1, 1, and then let me write 0, minus 12, minus 6, and 6. Okay, so you get that. All right, now we just say here you have minus 2, minus 1, 1. So you can get 1 here because in order to get, say, if you look at from the left, then the leading, you want to construct the leading one. That means this, we want this number to be 1. So you can divide through by negative 2 or just multiply negative 1/2. Okay? But here you have look at minus 12, minus 6, 6. Then you can tell that if you just multiply minus 6 and then add it to the third row, then you can just eliminate this part and also the rest of them. So what I did is that I used the operation 3 to minus 6. Okay? So that is the replacement of the third row. Okay? And that is the sum of the third row and minus 6 times the second row. Okay? So then this is just 6 times the second row, 6 times the second row, 6 times the second row. So if you add the minus 6 times the second row, you can get all zeros. Okay? That's why we have this. Okay? Okay, now, since we want to get the leading one, that's why we just multiply minus 1/2 to this. Then you get 1, 1/2, and minus 1/2. Okay? Then you get this. Then this is very close to the reduced row echelon form, but this is not yet a reduced echelon form. Okay? Because you have 1 here, this is leading one, so this is the column containing the leading one, but the fourth condition says that the leading one is the only non-zero entry in the column. Okay, column is a vertical one. Okay, so we want to have 0 here. Then what should we do? Just say subtract the second row from the first row. Okay, but we do not say we subtract. Okay, we say that add minus 1 times the second row to the first row. Okay? So 1, 2, semicolon minus 1, and you get this matrix. Okay? And just as we have checked last time, this is the reduced row echelon form, and we have now the reduced row echelon form here. So this 3 arrows means that I skipped some part of the reduction. Okay, so this is the reduced row echelon form. Let's check it. Okay, so the first condition is the first non-zero entry from the left of the each row is 1. Okay, and the all zero rows are collected down here. And then third one, the all leading entries going down as you go to the right. As you go down, then you go to the right. And then the leading one is the only non-zero in the column containing that leading one. So we have that. Okay, now the last part is already mentioned, so you can have it. Okay? So let me just write another way of expressing the solution. Okay? And we will use it very often in the next section. Okay. So here, if you choose z to be the free variable, okay, then you could write the solution like this. Okay. But we want to use some variable which is independent of x, y, and z. Okay. That is called a parameter. And so t is a parameter. Or free parameter. So just replace z by t. Then replace this z by t, then you can get this one. Okay? In this way, x1, y, and z can be written by just one free variable, in this case t. Okay? And that t is called a free parameter. Okay? If an augmented matrix of a linear system is obtained from an augmented matrix of another linear system by a sequence of elementary operations, if augmented matrices are row equivalent, then the two systems have the same solution set. Okay. So anyhow, this basically says that as far as you are keeping track with the elementary row operations, okay, then the solution set does not change. So I started out from this, and then wrote this. We obtained this system of linear equation. Okay. Then this proposition says the solution set of this system of linear equation and the solution set of this system of linear equation are exactly the same. Okay. So in that case, we call them equivalent. Okay. Why is that? That is why we are restricting our operation to be only 3 elementary operations. Okay? They are not the operations of the equations. They are operations of the rows of the matrix. But even so, if you interpret it, you can check easily that keep the solution set unchanged. Okay? That's why we can reach this. So this is also a very essential and very important technique of mathematics. Okay? We subdivided into a very small step, okay? And in each step, we just claim that some properties are kept. Okay? Then even if we just use that operation many, many times, in all the process, that property is kept. So that from the beginning to the end, nothing is changed as far as that property is concerned. Okay? So we just subdivide a big process into a small step. And we just examine the small step very carefully. Then we can tell that some properties are kept in that small step. And even if we have all sort of, say, many steps, we can tell that the property is kept in the whole sequence. Okay? All right? So this part I have already shown. Okay? Then I just explained how we can obtain reduced row echelon form. But this theorem guarantees us that we can always have a reduced row echelon form, and also it's in a unique way. Okay? So what does it mean? Every matrix is row equivalent to one and only one matrix in reduced row echelon form. Okay? This is wonderful. Okay? We cannot prove the validity of this theorem in this class, but it's not so difficult. Okay? So if you take a linear algebra 1, okay, then at the end you will be able to see the reason why this is so. Okay, so it's not extremely difficult, but I don't want to go through the proof of it in this class. Okay, so let me just repeat. Every matrix is row equivalent to one and only one matrix in reduced row echelon form. So in order to obtain the reduced row echelon form, there may be many ways. Okay, so for example, if I go from here to say Shibuya Station, okay, there may be many ways. Okay, there may be many ways. But something is kept unchanged. In this case, the destination, in this case, the reduced row echelon form, even if we can take many ways, the reduced row echelon form, if it is really a reduced row echelon form, okay, obtained from the original matrix by only 3 elementary operations, then the result is exactly the same. Okay, that is wonderful. Now, using that theorem, we define so-called rank. Okay, and this is a new concept which I didn't introduce last time. Okay, okay, so be careful. The number of non-zero entries of the reduced row echelon form of matrix A is called the rank of A, and write rank A. Okay. So this definition is a little bit tricky. Okay, so you have to be very careful. Okay. In this case, the last one. This is in reduced row echelon form. Okay. So let's call it A prime. Okay, why we call it A prime? Because it is related to A, but not exactly equal to A. Okay, so I wrote it A prime. Then, what is the number of non-zero rows of this A prime? That is, non-zero rows, so there are 2, right? So, rank of A prime is equal to 2. Okay, but this definition tells deeper thing. Okay, let's read it again. The number of non-zero rows of the reduced row echelon form of a matrix A is called the rank of A, and write rank A. Okay, that means, okay, this part is important. Okay, in this case, reduced row echelon form of this matrix is this matrix itself. Okay, because this is already a reduced row echelon form. Okay, but we know that this matrix is a reduced row echelon form of this matrix A. Then we say that the rank of A is equal to 2. Okay, look at that. Okay, there are 3 non-zero rows. There are 3 non-zero rows. But if you look at the definition of it, then the number of non-zero rows of not that matrix A, but of the reduced row echelon form of a matrix A is called the rank of A. Okay? So in order to find the rank of A, okay, in order to find the rank of A, we have to find the reduced row echelon form first, and then count the number of rows, non-zero rows. So in this case, this one, from this, even I myself cannot tell what the rank is. Okay? But after you reduce it to a reduced row echelon form, then I can tell, because this is a reduced row echelon form, and there are only 2 non-zero rows. Okay? So this is that. Okay? But is it ever possible? Is there any ambiguity? This theorem 2.2 guarantees that. Okay? Because if you start from this, okay, then you can reach the reduced row echelon form, unique reduced row echelon form. Okay? So from any matrix, okay, this is not the system augmented matrix. It can be any matrix, and then go to a reduced row echelon form. Then that is unique. Then you can also count the number of non-zero rows. Okay? So this matrix is given. Then the rank of that matrix is 2, because it's reduced row echelon form. Here you have 2 non-zero. You get it? So the definition of the rank is a little bit tricky. Okay? So it's not just counting the non-zero rows, number of non-zero rows, but first change into a reduced row echelon form, and then count the number of non-zero rows. Okay? Then I will give you one question. What is the rank of C? What is the rank of C? C is this matrix. Okay? Can anyone tell the rank of C? Okay, then the first, the kind of natural way is start from this C, okay, and then find the reduced row echelon form and count the number of non-zero rows. Okay? But this is just a part of the matrix set, right? So if you perform the elementary operation, then the last column is just that. So C is this part, and C is this part, C is this part, C is this part, and C is this part. Okay? So if you just use this C, and then with the same set of elementary operations, you can reach this. You can reach this. And is this kind of yellow, okay, part? Okay, is this a reduced row echelon form? Yes, it's a reduced row echelon form because the leftmost non-zero entry is 1, okay, and then all zero rows are collected at the bottom, and then the leading ones are going down as you go to the right, okay, and there is no zero entry at the column containing the leading one. Okay, so this is also a reduced row echelon form. Okay, so you don't have to say work over again to find the reduced row echelon form of C. Okay, if you know the reduced row echelon form of A, then you can find the reduced row echelon form of C as well. Okay, then what is the rank of C? Again 2, right? Just consider this box part, okay, yellow box part, then there are only 2 non-zero rows. Okay, just check it, okay? These are the examples. Okay, the first one, okay, please recall that last time we worked out from this augmented matrix of a system of linear equation, and then we found this, okay? So, if we assume that, then what is the rank of this? What rank of the first matrix? Okay. Then you just go down and reach the bottom, reach the last one. This is a reduced row echelon form. Okay. So what is the non-zero number of non-zero rows? That is 2. So the rank is 2. Okay. It's not because there are 2 non-zero rows in the first matrix, but because it has the 2 non-zero rows in the last matrix, which is the reduced echelon form of the first matrix. Okay, and then this one, what is the coefficient matrix? Coefficient matrix is the first part. Okay, then a coefficient reduced row echelon form of the first part is this 1, 0, 0, 1, and again the rank is 2. Okay, in this case, as I mentioned, the rank of this matrix is rank of this part, and that is 2. And rank of this part and rank of this part is equal to 2. And if you end up with having this type of thing, okay, this is the one you get if you replace this 17 to 16. That is just one of the examples I wrote on the board at the last time. Okay, so if you just start from 16, you get this. Okay. If you start with 16, you get this. Then, what is the rank of this? Then, that is 3. Okay? Now, in many cases, we have the same rank for the augmented matrix and the coefficient matrix. Okay? But in some case, you have a different ranks. Okay? Then what does it mean? Okay, so starting from this, I said that if this is not 17 but 16, you get this. Okay, then what is the equation of the last augmented matrix? Then the left hand side is 0, 0, 0. Okay, so that means 0x plus 0y plus 0z is equal to 1. Do you think it's possible? It's impossible, right? Right? So the left-hand side is 0, and you get 1 here. Okay, in that case, there is no solution and inconsistent. Okay, so if you have 0, 0, 0, 0, 1, okay, or the leading one is located at the last column, then that is a case the system is inconsistent. Okay, inconsistent meaning doesn't have a solution. Okay, and the next theorem tells us that if that is not the case, we have a solution. Okay, let me summarize in the theorem. Let A be an augmented matrix and C the coefficient matrix of a system of linear equations with n variables. Then the following holds. If the rank of A is not equal to the rank of C, okay, then no solution. Why is it? Okay, A is the augmented matrix and C is a coefficient matrix. The difference is just the last column. Okay, difference is just the last column. Okay, augmented matrix has the last column, and the coefficient matrix doesn't have one. Okay, so if the rank disagree, if the ranks do not coincide, okay, ranks are not equal, then you have to have 0, 0, 0, 0, 1, right? Because otherwise, some non-zero part is also included in that. Okay, so rank of A is not equal to rank of C. That means, and if you consider the reduced row echelon form, okay, it's important part is that the A, we are not looking at A or C, okay? But if you look at the reduced row echelon form of them, okay, then the rank are different only when A contains, a reduced row echelon form of A contains 0, 0, 0, 0, 1. Okay? But 0, 0, 0, 0, 1 means it doesn't have a solution, right? Because it's 0 equals 1. That is absurd. That's why if rank of A is not equal to rank of C, you can tell that the system is inconsistent. Okay? Then what about they are equal? Okay? If they are equal, and that is equal to n, what is n? Okay? N is the number of variables. Okay? Number of variables. And if they are equal and it's equal to the number of variables. In this case, it's not. So you have number of variables is 3. Okay? What is the rank? Rank is 2. Right? So in this case, rank of A is equal to rank of A prime and rank of C. It is equal to the rank of C. Okay? But it's not equal to the number of variables. Okay? But if it's equal, then the system has a unique solution. Because if it is, okay, for example, you have this type of thing, okay, then you can tell that x is 3 halves and y is minus 1 half. Okay? So in that case, unique solution. Okay? Please look at the example we have seen here. In this case, this is rank of A is equal to 2, and rank of the coefficient matrix is 2. And in this case, the number of variables is 2, right? So you have the unique solution. Then what if you have rank of A equals rank of C? That means that's consistent, and that is strictly less than n. That is the case we have dealt here. Okay? In that case, there are infinitely many solutions, and the general solution can be expressed with n minus rank A free parameters. Okay? In this case, variables are 3. Rank A is equal to 3 minus 2, so 1. So in this case, the solution can be expressed by one parameter. Okay? So that's why I said, okay, the rank is the number of non-zero rows, okay, of the reduced row echelon form. But that if you have a number of rows, then there are always exactly one leading coefficient, leading one. That means rank is equal to the number of leading ones. Okay, leading ones. In this case, there are two leading ones. If that doesn't agree with the number of variables, then you can find a kind of free column, right? And I said that you can choose that free column or the variable corresponding to the free column to be the free variable, right? That's why we can express the solution with n minus rank A free parameters. Okay? So in this case, infinitely many solutions. Okay, the number of solutions of a system of a linear equation is either 0, 1, or infinity. Okay? If we accept the theorem, then we can find that the number of solutions are either 0, that is the case we have inconsistent, or exactly 1, or infinitely many solutions, that is with free parameters. Okay? So there is no linear system having exactly two solutions. Okay? So I think in the quadratic equations, like x squared is equal to 2 or something, okay? Then you know that there are two solutions. Okay? So if it's a quadratic equation, then there is a possibility that you may have two solutions. But for the linear system, the number of solutions are either 0, 1, or infinity. You don't have any other cases. Okay? Let me just practice the way to write solutions. Okay? Let's look at the left-hand side. Theorem 2.3. Example 2.3. Okay, assuming that this is an augmented matrix of a system of linear equations. Okay, then firstly check that this is an, say, reduced row echelon form. Okay, firstly looking at from the left, all say non-zero entry, leftmost non-zero entry is 1, leftmost non-zero entry is 1, leftmost non-zero entry is 1, right? All 0 rows are collected at the bottom, right? And then the leading ones are going down as you go to the right, right? Staircase shape, okay? And then leading one is the only non-zero entry in the column, right? Those are the 4 requirements for the reduced row echelon form. Okay, so this satisfies that. Okay, then let's write out the solution. Okay, what is a solution? Okay, so I said that you just set, firstly you can write the equation like this: 1, 2, 3, 4, 5. 5 variables, so you can write it like this. Okay, then we take the free parameter to be the one which is not corresponding to the leading ones. Okay, so in this case you have leading ones at the first and third and fourth column. Okay, and the last one corresponds to the say right hand side. So there are 2 columns which do not have leading ones. Okay, so just take the free variable to be the variable corresponding to the columns which doesn't have a leading one. Okay, so in this case x2 and x5. Okay, so x2 is equal to t, x5 is equal to u. You can just choose arbitrary parameter. Okay, then you can write it in this way. Please check it. Okay, so x2 is equal to t, so x1 is equal to -1, -5t, and -5u. Okay, so important thing is if you choose the variables like this, parameters like this, you can just write all x1 up to x5 using a constant and the parameters you have chosen. Other variables, like in this case, x3 isn't here, x4 isn't here. Okay? That comes from the fact that we chose this augmented as a reduced row echelon form. That's why in the first line, x3 or x4 doesn't appear. Okay? That's why x1 can be written using only the free parameters we chose. Okay? So you can write it in this way. That last part we don't want to discuss today. Okay? So the third one, find solutions from the reduced row echelon form. Important thing is if you set n to be the number of variables, and the C is OA is the augmented matrix and C is a coefficient matrix. If they do not agree, the rank of A is not equal to rank A, then inconsistent. If rank of A is equal to rank of C and that is equal to the number of variables, then unique solution. Okay, one solution. And that is strictly less than n, then n minus rank A is the number of parameters you can choose. Okay, so that means you have that freedom to choose those numbers to express the solutions. Okay, the first step, find the augmented matrix and the coefficient matrix of a linear system and obtain the reduced row echelon form by elementary row operations, only 3 of them, and then find the solution, and the result is summarized below. Okay, so I'm afraid I don't have time to go through the exercises, but please check the solutions in the in my homepage with a link from Moodle. Okay, for example, this one says Quiz 2 2002. Okay, that means if you go to the Moodle and you follow the link to my homepage, then you can find Quiz 2 with a solution. Okay, so you can find the solution as well. Okay.